0.06 something. So I think it's probably 0.060. Which we've got, when you look up on the board, we've got two answers. So here we have the moment of inertia for the bat. That's 0.06 times the mass of the bat times the length of the bat squared. A moment of inertia will always have units of kilogram meters squared, so it should always be a mass times the length squared. So it should end with ml squared, like a mass times some size squared. The 0.0608 depends on the actual shape of the bat. Now, if you remember from last class, we took this circular roundish bat and we made a model for it where we said the handle part was thinner than the top. We said it was about half and half. And we get that value for the moment of inertia. Is this exactly the right shape of the bat? No. Could someone do a better job by breaking this up into 3 chunks? Sure. Instead of just having the bat suddenly get wider, they could have a little area in the middle where it got a little bit wider. Would the problem get a lot harder if you did it into 3 chunks? No, but it would take you about 50% longer, because now when you calculate your center of mass, you've got 3 chunks to deal with. When you do the moment of inertia calculations, you've got 3 chunks to deal with. So I've got 2 answers that went through to the end and got the correct value. Maybe some of the rest of you went through to the end, but it's not apparent up here if you got through to the end or not. So if you weren't able to get through the end, think to yourself, what got you stuck? What made it so that you couldn't get through to the end? I think maybe it's Max and Sean maybe got through to the end on their paper, maybe not.
Yeah.
Okay.
You know, we went through it, but then we realized I wrote down a half instead of the 12. Like which completely changed.
Okay. Well, this problem had, what do you think, 30 steps? If you broke down to little algebra things, 30 things to do. So if you do 30 things, you're going to make a mistake. If I do 30 things, I'm going to make a mistake. I've said my error rate's about 1 out of 20. Your error rate in life will probably come down a little bit as your brain gets better at checking things. But we found a couple of silly typos throughout. Like I think right here we left off an L squared. Over here I think we had 2 calculator errors. I think throughout the process though had 1 conceptual error, 1 legitimate misunderstanding. So let me review that misunderstanding again. I tried to visit with some of you separately on that. And that is, what is I wrong and what's I right? How do I know which is which for a problem? This formula right here that we derived last class, moment of inertia about the center of a rod, is 112 ml squared. For the little rod itself, for just the bottom half of the bat, if I wanted to calculate the moment of inertia for the bottom half of the bat only, about its center of mass, that is the correct way to do it. That would be I right. However, what is right for the little bottom section of the bat is not correct for the bat as a whole. For the bat as a whole, I need to figure out the moment of inertia about the center of mass of the bat, not the center of mass of the bottom half of the bat. So what was right for the bottom half of the bat wasn't right for the bat as a whole. So we had to take this formula, which is right for the bottom half of the bat, and make it wrong for the bottom half of the bat. Because I wanted to shift it to such a spot that was wrong for the bottom half of the bat, but would then be right for the bat as a whole. So I had to shift it to the center of mass of the bat, which required adding something to it. Let me try to explain it in one other way that will help you figure out should it be a plus or a minus sign. Suppose I wish to get my pencil rotating. And I want to rotate it like this. If I wish to rotate the pencil like this, call that case A, or get the pencil rotating like this, case B. Which of those cases do you think will be more difficult to get the pencil rotating? Case A, which will take more effort to get it rotating at 1 revolution per second? Case A or case B?
Case B.
Case B. Why will case B take more effort? Well, the mass is located further away from the pivot. So to get rotating at 1 revolution per second this way, since the mass is further away, that mass actually will be going faster to make 1 revolution per second than the stuff that's all really close to the pivot. So to get something going this way, I actually have to get the mass moving at a faster speed. So if you want to think of it in terms of energy, it's going to require more kinetic, it's going to have more kinetic energy, so it will take more work to do that. So it's going to take more effort to get it rotating this way. In fact, in general, the further the mass is from the center, the more effort it will take to get that object rotating. You can see that from the formula. I know there's a lot going on up here. We'll erase this right here. Our formula for the center of mass is this, or not center of mass, the moment of inertia, is the Ri squared times the individual chunk of mass. The bigger the distance is for that, from the center of mass to that chunk of mass, the bigger the contribution to the moment of inertia. So if I were to spin with my arms in like this, it's easy for me to get spinning. If I were to spin with my hands further out, it takes more effort to get myself spinning. Okay? So you learned some of those ideas in Physics 1. In fact, you learned about angular momentum, and if you pull your arms in towards the center, you are actually changing your moment of inertia. So if I am shaped like this, and I pull my arms in towards the center, will my moment of inertia go up or go down? So I start off like this, and I change shape, and now pull my arms towards the center. Will that cause my moment of inertia to go up or go down? Up. So Sean's saying up. So if you look at this formula, Ri squared m. Well, first, does my total mass change as I do this? No. So we're not changing the m's. What I'm changing is the r's. So if I go from this position to this position, did the distances from the masses to the center of mass go up or go down?
Down.
Down. So did the moment of inertia go up or go down when I went to do that?
Down.
Down. So when I change my shape to this, my moment of inertia will go down. Okay? What R is that? From where to where?
Center mass. Mass where the mass will be.
Excellent. That R is from the center of mass to that particular chunk of mass. Okay? If you are given a distance R showing up anywhere in any formula ever, if you are fuzzy on what that R means, if you can't answer the question, what does the R mean? If your only answer is it's a distance, then it means you're probably not understanding that formula. You have to be able to identify for a distance, it starts at this point, ends at that point. And R has a start and an end. So it's not just some fuzzy thing. So Edgardo's answer is very clear. It's from the center of mass to that particular point. Suppose I have a bike tire or a ring of any sort. The total mass of the bike tire is mt. The distance here is r. What is the moment of inertia of this bike tire?
R squared mt.
Yeah. So I'd add up all the individual chunks, but every chunk of mass is the same distance from the center. So every Ri would be capital R squared. If it's a constant, you can pull it outside the summation. And the sum of the individual masses, mi, is otherwise known as what?
Mt.
Mt. And there we go. So for a bike tire, my moment of inertia is, I have to find a marker that works. Mt r squared. For a disk, a solid disk of the same mass, mt. Do you you think the moment of inertia of a solid disk of the same mass and the same radius compared to the bike tire? Will the moment of inertia be higher or lower? Or the same?
Higher.
It'll be higher.
So I have a bike tire and a disc that have the exact same mass,
Lower.
and I'm trying to figure out the moment of inertia, whether it's higher or lower. So on average, is the distance from the mass of the disc closer to the center compared to the bike tire, or further from the center compared to the bike tire? Closer. So if it's closer to the center, then your moment of inertia is Ri squared Mi. So if the R's are smaller on average, that's going to cause the moment of inertia for this to go lower. So in the case of a solid disk compared to a bike tire, the solid disk is going to have a lower moment of inertia. We have a formula for the moment of inertia for a solid disk. We can get that integral of R squared dm. Add up these rings of mass. Each ring of mass, dm, could be written as the density times the volume. The density is a constant. The volume would be 2 pi r dr times the thickness. And you get rho times 2 pi t times the integral of r cubed dr from 0 to big R, which gives you 1/2 m total big R squared. I'm not going to fill in all the details because we did this one before. Okay, I'm just need you a quick 20-second overview of what that integral looks like. So to actually calculate the moment of inertia for the solid disk, I had to add up the contributions of all these little rings because each ring was the same distance away. And what we got was 1/2 times mt times r squared. So if I have two shaped wheels, both having the same mass, both having the same radius, but one is solid and one is hollow, the hollow one is going to have a greater moment of inertia because the mass is further to the outside. What does this have to do with the baseball bat? Well, let's look at two items. Here's the bottom handle of the bat. Okay? If I'm going to compare the moment of inertia of this bottom handle compared to point A or to point B. So I'm calculating the moment of inertia due to this mass, just this bottom bit, around point A or around point B. If I'm calculating the moment of inertia for that same amount of mass for these 2 points, on average the distances will be bigger to point B than they will be to point A. And therefore the moment of inertia will be bigger for around point B than around point A. So in our case we figured out the moment of inertia of the bottom part of the bat, and we wanted to figure out how does that contribute to the bat as a whole. So we're shifting from point A to point B. We're shifting away from the center of mass. Because we're shifting away from the center of mass, on average the distances are getting bigger. So our number has to be getting bigger, so that would have to be a plus sign, not a minus sign. The moment of inertia would be getting bigger, and that should give you a intuitive feel for whether that should be a plus sign or a minus sign, to try to help with your thinking through the problem. I noticed one group at one point had gotten a negative number for their moment of inertia. You can't get a negative value for moment of inertia. You can only do that if you had a negative mass, which we won't have in any of our applications. Nor will you ever encounter in life. So you can't get a negative value for the moment of inertia. So if you get a negative number, you know something's wrong. What would be bigger, the moment of inertia about point B or the moment of inertia about point C for the bat?
C.
C, correct. How about point A or point D? Which is bigger? The moment of inertia about point A or the moment of inertia about point D?
D.
D. In fact, the moment of inertia will be smallest. The smallest possible number you can get is around the center of mass. You can't do smaller than that. So the smallest possible moment of inertia is at point A. Any other point would be bigger than that. For the remaining 10 minutes today, I'd like to do another example. So the example I did last class involved the center of percussion. We had a formula